Alright, and welcome back to Geology, and this chapter is chapter 12 on the Earth's interior. So we're going to probe the Earth's interior, see what it's made up of, what it looks like. Most of our knowledge of Earth's interior comes from the study of earthquake waves, which we did in chapter 11. The travel times of P, the compressional waves, and the S, shear waves, through the Earth vary depending on the properties of the materials. If it's a fluid, if it's a solid, if it's a plastic. The variations in the travel times correspond to changes in the materials encountered. So, seismic waves, the velocity of them depends on the density and elasticity of the intervening material. Within a given layer, the speed generally increases with depth due to pressure forming a more compact material. The P waves, compressional waves, are able to propagate through liquids as well as solids, so the entire Earth can go through that. Now, as opposed to the compressional P waves, the S waves, shear waves, cannot travel through liquids. And we do know, we'll get into this more here in a minute, but we do know the interior of the Earth does have some liquid in it, near the core. So in all materials, the P waves travel faster than the S waves do, and seismic waves pass from one material to another. The path of the wave is bent. So how can the seismic waves tell us about the Earth's structure in the interior? We know that abrupt changes in seismic wave velocities that occur at particular depths help seismologists conclude that the Earth must be composed of distinct shells, and we call this differentiation. The layers are defined by composition. Because of the density sorting during an early period of partial melting, the Earth's interior is not homogeneous, meaning it's not all one material. So here's a good guess of what we think the Earth's interior is like. The orange is the mantle, which is kind of like a plastic. A plastic is something that can flow at one temperature and be a solid structure in another. So kind of think of like concrete, asphalt. They're plastics. And so the mantle is also a plastic. When it's hot, it can flow like a fluid, and when it's cooled, it can be solid like a rock. The yellow is the outer core, which we think is a liquid, metal, iron, and nickel. And the white is the solid inner core of iron and nickel. So we know we have three compositional layers in the Earth's interior. The crust is comparatively thin outer skin, can range from about 2 miles of the oceanic ridges thick to 40 miles in some mountain belts. So over continents, the crust is thicker than in the ocean. The mantle is a solid, rocky, silica-rich shell that extends to a depth of about 1,800 miles. The core is iron-rich sphere having a radius of about 2,100 miles. And the layers are defined by physical properties as well. With increasing depth, Earth's interior is characterized by gradual increases in temperature, pressure, and density. The layers are defined by other physical properties. Depending on the temperature and depth, a particular Earth material may behave like a brittle solid, or deform in a plastic-like manner, or melt and become liquid, as we mentioned before. The main layers of the Earth's interior are based on physical properties and hence mechanical strength. Layers are defined by lithosphere, which is the sphere of rock. That's the Earth's outermost layer, the crust, and the uppermost mantle. Relatively cool and rigid shell, inches about 100 kilometers in thickness, but maybe 250 kilometers or more in thick beneath the older portions of the continents and the mountains. The asthenosphere is beneath the lithosphere in the upper mantle to a depth of about 600 kilometers. It's a small amount of melting in the upper portion mechanically detaches the lithosphere from the layer below, allowing the lithosphere to move independently of the asthenosphere. The mesosphere means middle or lower mantle, rigid layer between the depths of 660 kilometers and 2,900 kilometers, roughly 500 to 1,800 miles. Rocks are very hot here and capable of very gradual flow. The outer core, a liquid layer composed mostly of an iron-nickel alloy, 1,400 miles thick, and a convective flow which generates Earth's magnetic field. So because the outer core is a liquid and a metal, and it flows, it generates its own magnetic field, and that's what causes the magnetic north and south poles on the Earth. And then finally, the inner core, a sphere with a radius of 2,100 miles, stronger than the outer core, and it behaves like a solid. Now, let's talk about some major boundaries inside the Earth. We call this the Moho discontinuity. It was discovered in 1909 by a gentleman named Mohoveric. Separates the crustal materials from underlying mantle and identified by a change in the velocity of P waves. The core and mantle boundary was discovered in 1914 by Gutenberg, based on the observation that P waves die out at 105 degrees from the earthquake in angle and reappear at 140 degrees. And so this 35-degree wide belt is named the P wave shadow zone, or just the shadow zone. So here we can see the P wave shadow zone. You can see where the waves go out, the direct P waves on your right there in the orange. And then you get to the kind of the red mantle, and it's kind of a quiet zone because it can't go through the core because it's liquid. And so there are places on the Earth where if an earthquake would happen at that star at top, we would not see those earthquake waves in the shadow zone. And so the core mantle boundary is characterized by bending or refracting of the P waves, and the fact that S waves do not travel through the core provide evidence for the existence of a liquid layer beneath the rocky mantle. And so here's that S wave shadow zone. The S waves cannot go through the liquid outer core. And so the discovery of the inner core was predicted by Lehman in 1936. P waves passing through the inner core show increased velocity, suggesting that the inner core is indeed a solid. Let's look at the crust in detail. The crust is the thinnest of Earth's divisions. It varies in thickness, can be thick under mountains and thin under the ocean. It has two parts, the continental crust. Average rock density is about 2.7 grams per cubic centimeter. The average density for the Earth is 5.5 grams per cubic centimeter. The composition of the continental crust is comparable to some felsic igneous rock. And then we have the oceanic crust. Density is a little higher, 3.0, composed mainly of the igneous rock basalt, lava rock. Inside, the mantle is 82% of the Earth's volume. It's a solid rocky layer. Upper portion has the composition of an ultramafic rock peridot. Two parts to it, the mesosphere, the lower mantle, and the asthenosphere, the upper mantle. The core is actually larger than the planet Mars. Its density is very high. Two parts to it, the outer core, the liquid layer, and the inner core, the solid inner sphere. The average density of the core is about 11. So when you take the crust at 2.7 and the core at about 11, it comes out to about 5.5 for the whole Earth. Mostly iron in the core, 5 to 10% nickel, and a little bit of some other elements. How did we get the core? Its origin, which most accepted explanation, is that the core formed early in Earth's history. And as Earth began to cool, iron in the core began to crystallize, and the inner core began to form. The requirements for the core to produce Earth's magnetic field are met in that it is made of material that conducts electricity, and it is mobile. The inner core rotates faster than the Earth's surface, and the axis of rotation is offset about 10 degrees from Earth's poles. So the north magnetic pole is a little bit away from the north pole of the Earth. Earth's temperature gradually increases with an increase in depth at a rate known as the geothermal gradient. This varies considerably from place to place, averages between 20 degrees Celsius and 30 degrees Celsius, so about 100 degrees Fahrenheit per kilometer in the crust, and this rate of increase is much less as you get deeper in. What contributes to the Earth's internal heat? The heat is emitted by radioactive decay, which we talked about last week, of uranium, thorium, and potassium. The heat is released as iron crystallized to form the solid inner core, and that heat released by colliding particles during the formation of the Earth 4.5 billion years ago. In the crust, we have a process called conduction, which is touching of physical materials, and the rates of heat flow in the crust vary. Inside the mantle, there's not a large change in temperature with the depth of the mantle. The mantle must have an effective method of transmitting heat from the core outward. So here we see convection in the mantle. It's kind of like a pot of boiling soup on a stove. The hot material rises to the top and then cools and sinks back down in a conveyor belt method. And then in the mantle, the convection we saw there, an important process in the Earth's interior. It provides the force that propels the rigid lithosphere plates around the globe. and moves the continents around. Because the mantle transmits S waves and at the same time flows, it's referred to as exhibiting plastic, both solid and fluid behavior, as I mentioned before. Let's look at Earth's gravity. Earth's gravity, 9.8 meters per second squared, changes at the surface due to Earth's rotation. The rotation causes a centrifugal force that is proportional to the distance from the axis of rotation. The shape is flattening slightly at the poles and resulting in a weaker gravity at the equator. Very slight difference. Let's look at seismic tomography. A three-dimensional image of structural variation within the mantle are made using seismic waves. The continental lithosphere can extend hundreds of kilometers into the mantle, and cold subducted oceanic lithosphere sinks to the base of the mantle, where plumes rise upward from the core and the mantle boundary. So here we can see these various temperature differences inside the Earth. We can look at the Earth's magnetic field. It's produced by the vigorous convection of liquid iron in the outer core. So here we have that liquid iron core. It's moving inside the Earth as the Earth rotates, and it generates that magnetic field. And it's also this magnetic field that generates the northern lights that we can see sometimes in the winter. The magnetic field sometimes randomly reverses. This is not a quick process, as some people would be led to believe. Some conspiracy theorists think that it happens very suddenly, and it does not. But the north and south poles do swap direction, and the reversal takes about a few thousand years to occur. The dipole field significantly decreases in strength, and reversals are very important in the field, as the field creates a magnetosphere around the Earth and protects our planet from solar winds. Without this magnetic field, the solar wind from the sun would send charged particles and disrupt our electrical grid. And sometimes it does if it breaks down the magnetic field strong enough. That's the end of chapter 12. So be sure to get on the quiz and discussion this week, and we'll see you next time.